Hello and welcome. Today I, Karthik Naik, will be presenting my paper on a fused geometric structural and control co-design framework for an energy harvesting kite. Now I'll go over a quick introduction to ocean kite systems. Marine hydrokinetic energy as a resource has tremendous potential, with the DOE estimating about 163 terawatt hours of usable ocean current energy annually. This has led to a large amount of research in ocean kite systems. Ocean kites are tethered mobile systems that are able to generate large amounts of tension through cross-current flight. The power is generated either by spooling or an onboard rotor. The focus of the literature, both in marine hydrokinetic kites and the sister field airborne wind energy systems, has been in the dynamic modeling and control aspects of the system. Given the complexities associated with closed-loop control of such a system, this focus is well deserved. However, plant optimization can significantly improve the power generation capabilities of the system. While geometric and structural considerations have been looked into before, they've not been studied along with control. We propose a combined geometric, structural, and control co-design framework that significantly improves power to mass ratio, an important techno-economic metric. This improvement is compared to a baseline. The, the design of the kite is similar to that of a glider in that it has two wings, a starboard and a port, a vertical and a horizontal stabilizer, and a fuselage. The attitude of the kite is controlled through actuation of three control surfaces: the ailerons, which induce a roll moment, the elevators, which induce a pitching moment, and the rudder, which induces a yaw moment. This work leverages a medium fidelity 6 degree of freedom model and a control system designed in our lab's previous works. The control system consists of a hierarchical controller that that tracks a prescribed path through control surface actuation commands, and a winch controller that switches strategically between spooling in and out at low tension and high tension respectively. The GIF here shows a sample simulation, and you can see that the green phase is when there is spooling out and power generation, and the red phase is respectively when there is spooling in and power is used. The image below shows a sample kite CAD. The cross section is also shown. This is a part of the design tool we've developed for optimizing the frame of the kite. The objective of the co-design problem is to maximize the power to weight ratio for a power requirement at a rated flow speed. As the power is constrained, this optimization reduces to minimizing the mass of the kite, subject to bounds on the decision variables, a performance constraint which requires a minimum generated power, and structural constraints on the wing and the fuselage. It also has a neutral buoyancy constraint, which is modeled as an inequality because cheap ballast mass can be added to attain this. The decision variables can be broadly classified into flight performance variables and structural optimization variables. They are the wingspan and aspect ratio, the fuselage diameter and length, the number of spars and the thicknesses of the spars, and the thickness of the wing shell and the fuselage shell. The co-design problem can be divided into three main subproblems. Each subproblem has been developed into an optimization tool that were eventually used in the proposed co-design framework. The first, the steady flight optimization tool, seeks to obtain the smallest wing that can deliver the required power. This is done through minimizing the volume of the wing that acts as a surrogate for the mass. The mass of the wing can be determined only with the structural decision variables like the number of spar or the thickness of the spar. This optimization is subject to two constraints, the performance and the geometric constraint. The left side of the performance constraint is what we term the ideal power, which denotes the theoretical maximum of achievable power in cross-current flight for a given flow speed. This was noted by a seminal paper by Miles Lloyd in 1980, which assumed that the kite in steady flight was in steady flight at an optimal angle of attack, which was flying directly downstream of the flow and can spool infinitely fast. As none of this is true, it gives rise to a flight efficiency term, which is defined as the ratio of the actual generated power to the ideal power. Knowledge of the flight efficiencies is important to accurately estimate the generated power. So why do we need a flight efficiency map? We've already seen that the ideal power is greater than the actual generated power due to closed loop flight dynamic inefficiencies and conversion losses. Having an efficiency map eliminates the need of running the controller in every optimization loop. The map was created through a sensitivity analysis, in which the wingspan and aspect ratio were chosen as the decision variables as they are most relevant to steady flight performance. Multiple kite designs with spans varying from 8 to 10 meters and aspect ratios varying from 6 to 14 were simulated and the efficiencies were mapped. This was then used to fit a surface to estimate a function of efficiency function of the decision variables. As they captured the behavior of the controller without actually running the controller, they can be termed as a control proxy function. This efficiency was then used in the performance constraint for calculations. This is the efficiency map that was generated in the design space. As you can see, the efficiency is high for wings with low spans and high aspect ratios. The second optimization tool is the structural wing design tool, which designs an optimized spar and shell structure for a maximum wing deflection. It receives the optimized span and aspect ratio along with the maximum hydrodynamic force from the steady flight optimization tool, which it uses to check for structural feasibility. The objective is to minimize the wing mass by varying the number of spars, the thickness of the spars, and the thickness of the shell. This is subject to foil geometry constraints, where the thickness of the spar and the shell are modeled as percentages of the root chord and the thickness of the foil, as well as a minimum moment of inertia constraint for a given load and maximum wing deflection. The frame is modeled with using small discrete rectangles which are integrated to take the shape of the foil. A sample output of the wing structure is shown with a chord of 1 meter and 3 spars. The third optimization tool is the structural fuselage design tool. Here, the fuselage frame is assumed to be a thin cylindrical shell. The objective is to minimize the mass of the cylindrical shell after receiving the maximum loads from the steady flight optimization tool. The decision variable is the thickness of the shell, which is modeled as a percentage of the diameter of the fuselage. This is subject to shear stress and hoop stress constraints, as well as normal stress and bending of the fuselage constraints. The three optimization tools are then integrated to form the core design framework. The first step is to form the efficiency map, where multiple kite designs in the design space are simulated with the closed loop flight controller and compared with the predicted power output to form the efficiency map or the control proxy function as a function of the plant decision variables. The next step is to actually run the plant optimization. First, the material foil properties are selected, as well as the power requirement and the rated flow speed. In an outer loop, the diameter and length of the fuselage are adjusted, in which first the steady flight optimization is run along which uses the control proxy function, which gives the optimal span and aspect ratio along with the loads on the wing, as well as the optimal diameter and length of the fuselage along with the loads on the fuselage. This is then used to adjust the structural decision variables to obtain an optimized wing structure and an optimized fuselage structure, which eventually gives an optimal kite. These results compare the performance of the baseline with the optimized kites, in which two cases were considered. One with an arbitrary efficiency of the baseline, which is at 0.48, and second, which uses the control proxy function or the efficiency map. No feasible structure was obtained for the baseline at a rated flow speed of 2 meters per second, where the resulting root chord was too small to obtain a feasible structural frame to handle the loads at that speed. There was no significant power drop moving from the baseline to the optimized kites, whereas the power to weight ratio, the relevant techno-economic, more than doubled from moving from the baseline to the optimized kite, whereas a further 22% improvement in the power to weight ratio was seen when the control proxy function was used. This slide illustrates and compares the designs of the baseline with the optimized kites. Note that the optimized with the control proxy function, which performs the best, has the least span and the least aspect ratio. These results compare the flight efficiencies observed during simulation of the baseline with the optimized kites. As you can see that there are similar peaks in flight efficiencies. However, the average flight efficiencies are higher for the optimized kites as the dips for the baseline are lower during the spool-in phase. These results compare the specific power or the power to weight ratio, which is the relevant techno-economic of the baseline with the optimized kites. Note that the mass of the kite is constant throughout the simulation, but the power varies, which causes the variation in the power to mass ratio. The negative power shown in the figure is when the power is consumed during the spool-in phase. In conclusion, the presented combined geometric, structural, and control co-design framework significantly increased power to mass ratio, the chosen techno-economic metric relative to a baseline design. The efficiency map generated serves as a control proxy function, which captures the plant control design coupling and eliminates the need to run the controller in the optimization loop. Future future work would be extension of this tool to account for other techno-economic metrics like site-specific flow characteristics or levelized cost of energy.